In September 2025, NASA stood before the world and described a single Martian rock as the closest humanity has ever come to discovering life on Mars. Then, almost immediately, its scientists urged everyone not to jump to conclusions. That rock is still sitting exactly where it was found, inside an ancient riverbed on Mars. We have no way to bring it home. Just a few months later, the mission designed to return samples like it was canceled, leaving one of the most important pieces of evidence in the search for life stranded on another world. The mystery does not end there. That same rock contains patterns that on Earth are overwhelmingly associated with microorganisms that obtain energy by reacting with iron. A retired Mars lander recorded seismic evidence suggesting an immense reservoir of liquid water buried deep beneath the planet's crust, enough to cover the entire surface more than a mile deep if it somehow reached the surface. NASA's Curiosity rover has repeatedly detected mysterious methane spikes that appear near the ground, mostly at night, rising to levels no one has been able to fully explain after more than a decade of investigation. Nearly 50 years ago, the first life detection experiment ever performed on another planet returned a result that has never been conclusively explained away. Individually, each discovery leaves room for doubt. Together, they refuse to disappear. Because this has never really been a question about Mars. It is a question about life itself. If life emerged independently on two neighboring worlds in the same solar system, then biology may not be a rare accident at all. It may be one of the universe's most ordinary outcomes. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. Let's talk about what we actually know. Imagine standing on Mars before its familiar red dust had claimed the landscape. Beneath a thicker sky, water gathered, flowed, and lingered across the surface with remarkable persistence. Valleys stretched between rising ground, rivers crossed ancient plains, and broad lakes rested inside enormous impact basins. The world before us would have felt surprisingly familiar, even though it orbited farther from the Sun than Earth ever has. Planetary scientists call this earliest chapter the Noachian period, the oldest geological era in Martian history. It was a time when Mars remained comparatively warm, rich in liquid water, and potentially hospitable by Earth standards. During this age, followed by the Hesperian period, rivers carved branching valley networks, while lakes collected inside craters that would much later become famous, including Gale Crater and Jezero Crater. Flowing waters shaped the terrain over immense spans of time. It left signatures that still survive. The story may reach even farther back. A crystal preserved inside the Martian meteorite, known as Black Beauty, formed about 4,450,000,000 years ago. Within that tiny mineral, researchers discovered evidence of hydrothermal activity, meaning hot water circulating through fractured rock during the planet's earliest history. Water may have been present almost from the beginning. That possibility reshapes everything we think we know. Geological evidence also points towards something even grander. Much of the northern hemisphere appears to have once held a vast ocean stretching across low-lying terrain. Such an ocean required conditions very different from those on present-day Mars. A denser atmosphere would have trapped more heat, while greater atmospheric pressure allowed liquid water to remain stable across broad regions instead of freezing or evaporating almost immediately. But no planet remains unchanged forever. More than 3 billion years ago, this watery world entered a long transformation. Water vapor gradually escaped into space as the atmosphere became thinner. The remaining water grew increasingly salty, making many environments progressively less welcoming. Lakes disappeared, rivers ceased their flow, the familiar frozen deserts slowly emerged. Even today, those vanished landscapes remain written into the planet's surface. Ancient shorelines, sediment deposits, and winding channels preserve a geological memory that no dust storm has erased. We can still trace the routes where rivers once wandered, following paths created billions of years before humanity ever looked toward Mars through a telescope. As we compare this ancient world with our own planet's distant past, another thought settles beside us. Life on Earth emerged during an era that shared striking similarities with early Mars. Both worlds possessed water, active geology, and environments capable of sustaining complex chemistry. If those ingredients proved enough here, what makes us so certain they failed there? Among every destination explored beyond Earth, one location rose above all the others after years of debate, mapping, and scientific scrutiny. Jezero Crater was never simply another landing site. It became the place where countless pieces of Martian history seemed to converge, offering one of the strongest opportunities our solar system has provided for discovering traces of an ancient living world. Around 3,500,000,000 years ago, Jezero Crater held a broad lake supplied by at least one substantial river system. That picture became even clearer when the National Aeronautics and Space Administration rover confirmed it through ground penetrating radar during the year 2024. This instrument, meaning a device that sends radio waves beneath the surface to reveal buried geological layers, uncovered structures consistent with sediments deposited beneath standing water. The western edge of the crater also preserves a remarkable river delta, where flowing water gradually slowed and spread its cargo across the lake. Those ancient deposits deserve special attention. On Earth, river deltas gather material from enormous drainage regions before laying it down layer upon layer. Organic matter becomes trapped alongside clay, sand, and fine sediment, creating natural archives capable of preserving chemical signatures across extraordinary stretches of time. If ancient Martian microbes ever existed upstream, a delta would have offered one of the best chances for preserving evidence of their presence. The river feeding this basin, known as Neretva Vallis, was once about 400 meters wide, which is about 1,312 feet. That immense channel hints at sustained water flow rather than occasional flooding. It carried minerals, sediments, and dissolved chemicals into the crater for long periods, steadily building the layered landscape that scientists hoped would retain a detailed environmental record. But reaching those records required patience. After landing during February of the year 2021, the rover spent years crossing the crater floor before finally climbing toward the rim, where some of the most scientifically valuable rocks awaited examination. Every carefully planned route balanced engineering limits against geological promise, allowing each new outcrop to reveal another chapter of the crater's complex history. Fresh discoveries continued reshaping that story. During January of the year 2026, researchers from Imperial College London concluded that Jezero experienced a far more intricate history of water than previously believed. Their analysis suggested ancient beaches formed along shifting shorelines, while groundwater continued circulating beneath the surface long after visible lakes had changed or disappeared. Water moved across both space and time in ways earlier models had underestimated. You can see why this destination earned such extraordinary attention. Jezero Crater represents far more than an attractive geological landmark. It preserves the layered remains of a long lived aquatic environment shaped by rivers, lakes, sediments, and underground water. Among every known location explored beyond Earth, Few places offer a stronger possibility that the planet's oldest biological clues, if they exist at all, may still be waiting within the stone. Discovery sometimes arrives without spectacle. It begins with a single object that appears ordinary until every instrument aimed toward it starts revealing another layer of unexpected complexity. That moment came on the 21st of July, during the year 2024, when the National Aeronautics and Space Administration rover examined a partly buried rock resting inside the Bright Angel Formation along an ancient dry riverbed. Scientists gave the rock the name Cheyava Falls. At first glance, it looked like another weathered fragment preserved within Jezero Crater. Closer inspection transformed that impression. The stone showed unmistakable signs that liquid water had once moved across its surface. Organic molecules were also present, adding another important ingredient to an already intriguing setting. Then researchers noticed something even stranger scattered across the exposed face of the rock. Tiny markings appeared throughout the stone, each measured only a few millimeters across, meaning just a fraction of an inch. Bright centers were surrounded by darker rings, creating patterns that resembled the spots covering the coat of a leopard. They were distributed across separate locations rather than blending into one continuous layer. Every spot suggested a localized chemical process that had unfolded inside the rock long ago, leaving behind distinct mineral boundaries. But the arrangement itself drew the greatest attention. On Earth, comparable patterns commonly form where microorganisms obtain energy through reactions involving iron-rich minerals. Those microscopic organisms alter the surrounding chemistry as they grow, producing halos that closely resemble what appeared inside Cheyava Falls. Geology can also create complex mineral textures, and researchers continue evaluating those possibilities with great care. Even so, this specific combination remains remarkably uncommon without biological participation. The rock itself added another layer to the puzzle. Cheyava Falls measured about 1 meter, which is about 3 feet, in length and roughly zero point 0.6 meters, that is nearly 2 feet, across. Its arrow-shaped outline stood apart from surrounding rocks, while its partial burial preserved sections that had experienced less exposure to the harsh Martian surface. During more than 3 years of exploration, the rover had never encountered another specimen quite like it. Every observation strengthened scientific interest without crossing the threshold into certainty. Water had once flowed here. Organic molecules survived within the stone. Iron-bearing minerals concentrated into unusual patterns. Each clue alone could arise through ordinary geological activity. Together, they formed a combination worthy of extraordinary attention. Eventually, the decision became unavoidable. The rover extended its robotic drill and removed a carefully selected core from the interior of Cheyava Falls. That sample received the name Sapphire Canyon before being sealed inside a titanium collection tube designed to preserve it for eventual study on Earth. Today, that tube remains exactly where it was collected, resting on Mars, carrying within it one of the most compelling pieces of evidence ever gathered in humanity's search for another origin of life. Before we travel any deeper into the evidence, we need to slow our pace for a moment and understand a single word that guides nearly every search for life beyond Earth. That word is biosignature. You will hear it often in planetary science, yet its meaning is more careful and restrained than many people imagine. A potential biosignature is any substance, pattern, or structure that could have been produced by living organisms, but still requires additional evidence before scientists can conclude whether life was truly responsible. The word potential carries enormous weight. It reminds us that nature often creates similar results through very different processes. Every promising clue must survive years of testing before it earns greater confidence. Some biosignatures are chemical. Living organisms manufacture certain compounds, yet geological reactions can sometimes produce those same chemicals without biology playing any role. Others are structural, meaning they involve shapes, textures, or mineral arrangements that appear overwhelmingly linked to living activity on Earth. A third category involves isotopic ratios, which are subtle differences in the forms of chemical elements. These ratios can shift when organisms process matter, leaving behind recognizable chemical fingerprints. None of these categories stands alone with absolute certainty. But Chayava Falls attracted such careful attention because several independent clues appeared together within one ancient rock. Scientists found evidence that flowing water had shaped the environment. Organic carbon, the fundamental chemical framework of every known living organism, was present. The surrounding minerals included iron phosphate and iron sulfide, both capable of participating in chemical reactions that release usable energy. Researchers also identified textures resembling reaction fronts, meaning narrow boundaries where chemical changes progressed through the rock over time. Each observation remained explainable without life. Together, they created an unusually compelling combination. That convergence matters because astrobiologists, scientists who study the possibility of life beyond Earth, follow an unwritten standard unlike almost any other field of research. The burden of proof approaches impossibly high levels. A mistaken announcement claiming extraterrestrial life would become one of the greatest scientific errors ever recorded. Extraordinary caution protects scientific credibility as much as extraordinary evidence advances discovery. This careful approach shaped the peer-reviewed paper published in the journal Nature during September of the year 2025. After examining every plausible geological explanation available, the researchers concluded they found no especially strong evidence supporting the currently proposed non-biological mechanisms responsible for producing the observed patterns. But they stopped there. They did not eliminate those possibilities entirely. That distinction may sound subtle, yet it changes everything. Scientists were not declaring victory in the search for life. They were acknowledging that the evidence deserved every available tool, every competing hypothesis, and every future investigation. A biosignature is never a verdict by itself. It is an invitation to keep looking with greater precision than ever before. Inside the Sapphire Canyon sample lies a chemical inventory that scientists describe with remarkable restraint. Every mineral, every atom, and every microscopic layer has become part of a larger conversation. You can almost picture researchers weighing each observation with extraordinary care, knowing that every conclusion must survive relentless examination before it earns lasting confidence. The sedimentary rocks surrounding Chayava Falls contain abundant clay and silt. These fine-grained materials are far more important than they first appear. Clay has an exceptional ability to trap organic material between its microscopic layers, shielding delicate compounds that might otherwise break apart over immense spans of time. Silt helps preserve that record by gently burying and protecting what settles within it. On Earth, environments rich in clay and silt often preserve some of the oldest microbial evidence ever discovered. The chemistry extends much further. Scientists identified organic carbon throughout the formation. Organic carbon forms the chemical backbone of every known living organism, from the smallest microbe to the largest animal. Sulfur and oxidized iron also occur together within the rock. These elements can create what researchers call a redox couple, meaning two chemicals that exchange electrons during a reaction. That exchange releases usable energy. Many microorganisms on Earth survive entirely by exploiting these natural chemical gradients rather than relying on sunlight. Phosphorus completes another important part of the picture. This element is essential for ribonucleic acid, and the molecules cells use to store and transfer energy. Without phosphorus, the chemistry supporting every known living cell becomes extraordinarily difficult to sustain. Finding it alongside the other ingredients naturally captured scientific attention. But no single ingredient tells the whole story. Joel Hurwitz of Stony Brook University, the lead author of the Nature study examining Cheyava Falls, concluded that this combination of compounds could have provided a rich energy source for microbial metabolisms. A metabolism is simply the collection of chemical reactions that allows an organism to obtain energy and remain alive. The environment recorded inside this rock appears capable of supporting exactly those kinds of reactions. That possibility points toward a remarkable group of organisms called chemolithotrophs. The name describes microbes that obtain energy directly from rocks and minerals instead of sunlight. They survive by driving chemical reactions involving iron, sulfur, and other naturally occurring elements. On a planet where surface conditions eventually became harsh and photosynthesis may never have flourished, organisms like these represent one of the most realistic biological models scientists can imagine. Even now, caution remains essential. Every chemical found inside Cheyava Falls can arise through ordinary geological processes without any living participation. Minerals can assemble, organic compounds can form, chemical gradients can emerge naturally, but researchers continue returning to the same observation. This precise collection of ingredients appears together within one carefully preserved setting, shaped by ancient water and unusual mineral textures. Whether that remarkable convergence reflects biology or geology remains unknown, and today no instrument on Mars can settle that question with certainty. While one rover examined the ancient remains of Jezero Crater, another continued its patient journey across a very different landscape. Far away, inside Gale Crater, about 3,700 kilometers away, which is about 2,299 miles. The Curiosity rover had already spent years exploring layers of rock that recorded another chapter of Martian history. Then, during April of the year 2026, its findings added an entirely new dimension to the search. Curiosity investigated clay-rich sandstones that formed roughly 3,500,000,000 years ago. These rocks became the site of the first detailed chemical experiment of its kind ever performed on another planet. Using an onboard laboratory designed to identify complex compounds released from carefully heated samples, scientists detected an unexpectedly rich collection of organic molecules preserved within the ancient sediments. More than 20 different organic compounds emerged from the analysis. Among them were trimethylbenzene, naphthalene, benzothiophene, and methylnaphthalene, molecules that rarely attract public attention but immediately captured scientific interest. Organic molecules are carbon-based compounds that serve as the building blocks for every known living organism. They can also arise through entirely natural geological processes. Their presence alone cannot reveal which path created them. But one discovery stood apart from the rest. Researchers identified a molecule resembling one of the chemical building blocks used to construct deoxyribonucleic acid. That resemblance carried profound implications without offering definitive answers. It did not demonstrate that Martian organisms once existed, nor did it prove those compounds arrived from meteorites or formed through ordinary planetary chemistry. Instead, it expanded the range of possibilities that scientists must now investigate with even greater care. The broader picture became increasingly difficult to ignore. Curiosity and the Perseverance rover explored locations separated by enormous distances, each with its own geological history and environmental conditions. Yet, both missions uncovered complex organic chemistry preserved within ancient rocks of similar age. That growing pattern suggested these compounds might not represent isolated curiosities confined to one fortunate landing site. They could instead reflect processes that once operated across wide regions of early Mars. Even so, an important limitation remains. Curiosity excels at detecting molecules hidden inside rock, but it cannot determine exactly how those molecules formed. The instruments carried aboard any rover must survive launch, interplanetary travel, landing, years of operation, and the severe conditions of Mars. Those engineering demands place strict limits on their size and sensitivity. Laboratories on Earth operate under no such constraints. Their mass spectrometers, electron microscopes, and isotope analysis instruments possess capabilities many orders of magnitude beyond what any robotic explorer can carry across space. Curiosity can reveal that something remarkable is present. It cannot identify its ultimate origin. That final distinction still depends upon samples reaching Earth, where the smallest chemical details can finally be examined with the precision this extraordinary question demands. Few discoveries on Mars have inspired as much debate as a gas that should barely be there at all. Methane has become one of the longest running and most divisive puzzles in planetary science, frustrating researchers for more than a decade because every new observation seems to complicate the story rather than simplify it. The first surprise arrived when the Curiosity rover measured a sudden methane concentration roughly 10 times higher than the normal background level. Then, only a few months later, the signal faded almost completely. Since that initial event, the rover has recorded 6 additional methane spikes, each appearing unexpectedly before disappearing again. Scientists searched for confirmation using orbiting spacecraft capable of examining the atmosphere on a global scale, yet those measurements failed to reveal a matching pattern. The planet seemed to be telling two different stories at once. But the behavior of Martian methane became even stranger. The gas appears mainly during the night. Near the surface, it rises and falls with the seasons. At times, local concentrations climb to around 40 times the usual background level before dropping once more. Higher in the atmosphere, however, methane remains largely absent. Other landing sites have also failed to detect comparable amounts close to the ground. Each new measurement deepened the mystery instead of resolving it. This matters because methane occupies a unique place in the search for life. On Earth, the overwhelming majority of atmospheric methane originates from living organisms. Among the best known producers are methanogens, microscopic organisms that generate methane as a byproduct of their metabolism. A metabolism is the network of chemical reactions that provides an organism with usable energy. These microbes require neither sunlight nor oxygen, allowing them to thrive in environments that appear extremely hostile to more familiar forms of life. But biology is only one possible explanation. Recent research suggests that natural changes in atmospheric pressure may draw gases upward from underground reservoirs, allowing buried methane to escape into the thin Martian atmosphere. Another competing idea focuses on salty soils rich in perchlorate. Scientists propose that these crusts could trap methane beneath the surface before gradually breaking apart and releasing the gas during changing environmental conditions. Then another possibility emerged that few expected. During the year 2025, researchers suggested that at least some methane detections might have resulted from tiny leaks inside Curiosity's own scientific instrument. If even a fraction of the recorded methane came from the rover itself, separating genuine Martian signals from engineering artifacts becomes even more challenging. Yet none of these explanations has settled the matter. Geological chemistry remains plausible. Instrument contamination cannot be dismissed completely. Biology also remains on the table. Every proposed solution accounts for part of the evidence while leaving important observations unexplained. We are left with a puzzle that refuses to yield a simple answer, where every new study narrows certain possibilities while opening unexpected ones, and where the possibility of living microbes beneath the surface still cannot be confidently ruled out. What if the largest body of liquid water on present day Mars is completely invisible from the surface? That possibility emerged during the year 2024 when researchers studying seismic records proposed one of the most remarkable ideas in the history of Martian exploration. Rather than searching across frozen plains or beneath polar ice, they looked deep into the planet itself. During August of the year 2024, scientists analyzed measurements collected by the National Aeronautics and Space Administration InSight Mars lander. The lander carried an instrument that recorded seismic waves, meaning vibrations traveling through the planet after Marsquakes and meteorite impacts. Those waves behave differently depending on the materials they cross. Solid rock transmits them one way. Rock filled with liquid water changes both their speed and their path. The measurements pointed toward a broad zone lying between roughly 10 kilometers, which is about 6.2 miles, and 20 kilometers, which is about 12.4 miles, beneath the Martian surface. Instead of behaving like completely solid crust, this region appeared consistent with fractured basalt saturated by liquid water. Basalt is a volcanic rock that forms when molten material cools. If countless fractures inside that rock are filled with water, seismic waves slow in characteristic ways that researchers can recognize. The study, published in the Proceedings of the National Academy of Sciences, suggested an astonishing possibility. If that hidden reservoir were spread across the surface, it could contain enough water to cover the entire planet to a depth exceeding 1 mile. That is an amount comparable to the volume of Earth's oceans, preserved far below a landscape that appears dry beyond recovery. But another investigation strengthened the picture. During the year 2025, researchers from the Chinese Academy of Sciences and the Australian National University identified a broad, low-velocity layer within the upper crust. A low-velocity layer simply means a region where seismic waves travel more slowly than expected. Their analysis placed this zone between about 5.4 kilometers, that is nearly 3.4 miles, and 8 kilometers, which is about 5 miles, beneath the surface. They estimated that this porous, water-saturated region could hold the equivalent of between 520 meters, which is about 1,706 feet, and 780 meters, which is about 2,559 feet of global water coverage. If that hidden water contains dissolved salts along with sulfur and iron, the chemistry becomes especially intriguing. Those ingredients can produce chemical energy through natural reactions, creating environments similar to the deep underground habitats where microorganisms thrive on Earth without sunlight. Everything depends upon whether these interpretations prove correct. Yet if they do, the image of Mars changes profoundly. We are no longer looking at a planet that merely remembers water. We are looking at one that may still contain an active liquid interior beneath its frozen crust. On Earth, every confirmed environment holding persistent liquid water has eventually revealed life. Mars has not yet answered whether that pattern continues, but it has become much harder to dismiss the possibility. The strongest argument for life beneath the Martian surface does not begin on Mars at all. It begins far below our own feet, in places where no sunlight has ever reached, and where entire ecosystems exist beyond the influence of the world above. These hidden environments have transformed how we think about where life can persist. Scientists call this hidden realm the deep biosphere. A biosphere is simply a region where living organisms exist. Unlike forests, oceans, or grasslands, the deep biosphere extends several kilometers beneath Earth's surface, where microorganisms inhabit cracks and pores inside ancient rock. They live without sunlight, without fresh air, and often without any meaningful connection to the surface for thousands or even millions of years. Their survival depends upon chemistry rather than light. Water slowly reacts with surrounding minerals, releasing energy-rich compounds that microorganisms can exploit. Instead of relying on photosynthesis, the process through which plants convert sunlight into usable energy, these organisms obtain everything they need from reactions occurring naturally between water and rock. The source of life becomes geology itself. One of the most remarkable examples lies within the Witwatersrand gold mines of South Africa. Researchers discovered living microorganisms about 3.4 kilometers underground, which is about 2.1 miles, inside water that had remained isolated from the surface for roughly 12,000 years. Those microbes survived by using hydrogen generated as water interacted with ancient rocks deep below the surface. Their habitat remained stable across timescales that exceed the entire history of human civilization. But these organisms are often misunderstood. Popular discussions frequently compare possible Martian life with creatures such as tardigrades because they tolerate harsh environments. That comparison overlooks something more relevant. The organisms that matter here are chemolithotrophs, microorganisms that obtain energy directly from minerals. Many use sulfate instead of oxygen during their metabolism, allowing them to flourish where oxygen never penetrates. They require neither sunlight nor plants nor surface ecosystems. Their world operates according to entirely different rules. When we compare those habitats with conditions proposed beneath Mars, the similarities become difficult to ignore. Liquid water may occupy fractured volcanic rock. Sulfur and iron appear available for chemical reactions. Internal planetary heat still exists beneath the crust. Those ingredients create redox chemistry, meaning natural exchanges of electrons that release energy usable by microorganisms. On Earth, those exact conditions already support thriving microbial communities. None of this demonstrates that living organisms currently inhabit the Martian underground. That conclusion remains beyond the available evidence, but it changes the nature of the discussion. We are no longer asking whether life could survive under impossible conditions. We already know life does exactly that on Earth. If biology ever emerged during Mars's more hospitable past, the deep crust offers something the surface no longer can. It provides water, chemical energy, protection from radiation, and extraordinary stability across immense spans of time. Should any ancient descendants remain, this hidden world beneath the frozen landscape is where we would expect them to endure. Every habitable world depends upon more than water alone. Around a planet, invisible forces can determine whether rivers endure for billions of years or vanish into memory. For ancient Mars, one of those unseen guardians may have mattered more than anything else. It surrounded the planet long before its lakes disappeared, then gradually faded away. Early in its history, Mars possessed a global magnetic field much like Earth's. A magnetic field is created when electrically conducting material moves within a planet's interior, generating invisible lines of force that extend into space. That protective envelope deflected much of the solar wind, the continuous stream of charged particles flowing outward from the sunday. As long as the magnetic field remained active, the atmosphere enjoyed a substantial measure of protection. But that shield did not last. Around 4 billion years ago, the magnetic field collapsed. Scientists continue debating the exact sequence of events, yet the leading explanation centers on the planet's interior. Mars gradually cooled. Its once active liquid iron core began to solidify. As internal motion weakened, the process generating the magnetic field also faded until the planet could no longer sustain a global magnetic barrier. The consequences unfolded across immense stretches of time. Without that invisible protection, the solar wind interacted directly with the upper atmosphere. Particle by particle, the atmosphere escaped into space. This was never a single catastrophic event. It happened gradually, over millions of years, slowly reshaping the entire planet. As atmospheric pressure declined, liquid water became increasingly unstable at the surface. The greenhouse effect also weakened. A greenhouse effect occurs when gases in an atmosphere trap heat that would otherwise escape into space. With fewer gases remaining overhead, temperatures continued falling until broad regions stayed below the freezing point of water. Oceans diminished, lakes vanished. Some water froze beneath the ground, while other portions escaped into space altogether. But the timing of this transformation carries extraordinary significance. Geological evidence suggests Mars remained potentially habitable for somewhere between 300 million and 700 million years before conditions deteriorated beyond recognition. That interval may sound brief beside the age of the solar system, yet it exceeds the estimated time required for life to emerge on Earth after our own planet became habitable. This comparison changes the conversation. We are no longer imagining a world that lost its chance before chemistry could begin. Mars appears to have possessed a window long enough for the earliest biological processes to unfold if the necessary ingredients came together. The deeper mystery, therefore, becomes one of survival rather than possibility. If life gained even the smallest foothold before the magnetic shield disappeared, what happened next? Did every organism vanish alongside the lakes and rivers, or did some retreat into environments protected from the collapsing climate? The disappearance of the magnetic field may explain why Mars changed so dramatically. It does not necessarily explain whether every trace of life disappeared with it. It is easy to picture Mars as a planet that simply dried out. Rivers disappeared, lakes vanished, and every remaining drop escaped into space. But the evidence now tells a more complicated story. Much of the water never truly left. Instead, it changed where it lived and the form it took. Across the Martian surface, more than 5 million cubic kilometers of ice have already been identified. That is enough frozen water to blanket the entire planet beneath a layer about 35 meters deep, which is about 115 feet. Rather than disappearing altogether, an enormous fraction of Mars's ancient water became locked within ice sheets, buried glaciers, and frozen ground that still survive today. The largest reservoirs lie at the poles. Their existence is beyond dispute. The southern polar ice cap alone contains enough water ice that, if melted and spread evenly across the planet, it would cover Mars beneath approximately 11 meters of water, which is about 36 feet. Similar deposits occupy the northern polar region, preserving a frozen archive built layer upon layer across immense stretches of planetary history. But ice stores more than water. It can preserve chemistry as well. Laboratory experiments have shown that important molecular building blocks of proteins can remain intact for tens of millions of years when trapped inside exceptionally pure ice, even while exposed to relentless cosmic radiation. Ice acts as a remarkably effective shield, slowing the chemical damage that gradually destroys fragile organic compounds over time. That realization has reshaped scientific priorities. Earlier searches often focused on exposed rocks or dusty sediments weathered by billions of years at the surface. Increasingly, researchers argue that the greatest rewards may come from drilling into clean buried ice, where ancient molecules could remain protected far longer than anywhere exposed to the open environment. The search is gradually shifting beneath the frost instead of across it, but the frozen poles represent only one chapter of the story. Beneath the surface lies widespread permafrost, ground that remains permanently frozen while preserving additional stores of water. Far deeper still, seismic evidence suggests a fractured layer saturated with liquid water within the Martian crust. Together, these discoveries describe a planet that retained water in several different forms across billions of years. Rather than a vanished relic, Mars appears to have maintained a slow planetary water cycle, frozen near the surface while remaining active far below. Seen this way, the planet never became completely dry. Water continued moving between ice, frozen ground, and deeper reservoirs as conditions evolved. Habitable environments, therefore, may never have disappeared entirely. They simply retreated beyond easy reach. That perspective transforms the central question. We are no longer asking whether Mars once possessed water. We know it did. We are asking whether anything alive existed while those environments were most favorable, and whether any descendants adapted as the planet slowly concealed its remaining water beneath an increasingly frozen world. Finding organic molecules on Mars sounds almost expected today, yet the reality remains deeply surprising. Every day, the Martian surface endures an assault that should steadily erase delicate carbon-based chemistry. Ultraviolet radiation pours down without the protection of a thick atmosphere, while energetic cosmic rays penetrate the ground itself, breaking apart molecular structures over time. Near the surface, most exposed organic compounds should deteriorate within only thousands of years. That expectation makes every confirmed discovery more significant. Organic molecules have emerged from ancient rocks inside Gale Crater. Comparable carbon-bearing compounds appeared within Chayava Falls. Additional discoveries have come from clay-rich sandstones, formed roughly 3.5 billion years ago. Instead of isolated hints, we are beginning to see a repeated pattern spread across different locations and different geological settings. But these molecules did not survive through chance alone. Much of their endurance appears to depend upon clay minerals known as phyllosilicates. These minerals form extremely thin, layered structures that can trap tiny organic molecules between microscopic sheets of rock. Once enclosed, the surrounding mineral acts as a protective barrier, greatly reducing exposure to damaging radiation. On Earth, the same process preserves traces of ancient organic material inside shale formations that have remained buried for immense spans of geological time. That connection has become increasingly important for Mars science. After discovering organic compounds within ancient clay-rich rocks, The Curiosity mission team concluded that the Martian surface is capable of preserving molecules that could serve as potential signs of ancient life. This does not establish a biological origin. It demonstrates something equally essential. Mars possesses natural storage systems capable of protecting fragile chemistry across billions of years. Another complication emerged only after scientists better understood the planet itself. Martian soil contains roughly 1/2 of 1% perchlorate, a strongly oxidizing salt. An oxidizing substance is one that readily drives chemical reactions capable of breaking apart complex molecules. When soil containing perchlorate is heated during laboratory-style experiments aboard a spacecraft, many organic compounds are destroyed before instruments can identify them. That realization transformed the meaning of much older results. The Viking landers reached Mars during the 1970s and searched directly for organic material within the soil. Their instruments detected essentially none, leading many researchers to believe the surface lacked meaningful carbon-based chemistry. But those experiments heated the samples, exactly the condition now known to activate, perchlorate, and destroy delicate organics before they could be measured. Seen from today's perspective, that historical conclusion becomes far less certain. The absence of detected organics may never have represented an empty planet. It may have reflected the limits of the technology available at the time. Rather than revealing a barren landscape, those pioneering experiments may have unintentionally erased part of the very chemical record they had traveled across space to examine. Long before today's rovers crossed ancient riverbeds and drilled promising rocks, humanity attempted something even more ambitious. We asked Mars a direct question. We wanted to know whether anything there was alive. Nearly 5 decades later, the answer remains remarkably difficult to interpret. In the year 1976, the Viking 1 and Viking 2 landers reached different regions of Mars, separated by roughly 4,000 miles, which is about 6,437 kilometers. Each spacecraft carried a collection of scientific instruments designed to investigate the planet itself, but several experiments had an even greater purpose. They searched directly for evidence of living organisms within the Martian soil. The most famous investigation became known as the labeled release experiment. Scientists added a small amount of water containing nutrients mixed with radioactive carbon into samples of Martian soil. If microorganisms consumed those nutrients, they could release radioactive gas as a byproduct of metabolism, the collection of chemical reactions that allows living organisms to obtain energy and survive. On Earth, that response would strongly suggest biological activity. The results surprised almost everyone. The experiment produced a positive signal. Even more remarkably, both Viking landers generated similar responses despite operating thousands of miles apart. The measurements were repeatable, consistent, and carefully verified. Taken alone, they resembled exactly the kind of outcome researchers had hoped to find. But another instrument complicated the story. A separate experiment searched for organic molecules inside the soil and detected essentially none. Without organic material, many scientists argued that living organisms could not reasonably explain the labeled release results. Attention shifted toward unusual chemistry instead. Highly reactive compounds within the soil became the leading explanation, producing gases through purely chemical reactions after contact with the nutrient solution. The debate never truly ended. Gilbert Levin, the principal investigator responsible for the labeled release experiment, spent the remainder of his career arguing that Viking had indeed detected living microorganisms. His interpretation never became scientific consensus. Yet neither was it conclusively disproved. The observations themselves remained exactly as the instruments recorded them. But the picture changed again decades later. During the year 2008, later missions confirmed that Martian soil contains perchlorate, a strongly oxidizing salt. Scientists soon recognized an important consequence. Heating perchlorate during laboratory-style analysis can destroy delicate organic molecules before instruments detect them. That realization offered a new explanation for why Viking failed to identify organics, even if such molecules had actually been present within the samples. Today, the Viking results occupy an unusual place in planetary science. They have never demonstrated the existence of life on Mars. They have also never received a universally accepted, non biological explanation that resolves every observation. After nearly 50 years, the first dedicated search for life on another planet remains technically unfinished, its central question still waiting for an answer that satisfies every piece of evidence. Long before today's discoveries reshaped the conversation, another piece of Mars captured the world's imagination. It never landed with a spacecraft. It arrived after an extraordinary journey through space, eventually coming to rest within the frozen landscape of Antarctica, where researchers recovered it from the Allen Hills region during the year 1984. The meteorite became known as Allen Hills 84001. About the size of a potato, it appeared unremarkable at first. But trapped inside the rock were tiny pockets of gas whose composition closely matched measurements of the Martian atmosphere. Those chemical fingerprints left little doubt. The stone had once been part of Mars before an ancient impact blasted it into space, where it wandered for millions of years before falling to Earth. Everything changed during August of 1996. Scientists announced that the meteorite contained microscopic structures resembling fossilized microorganisms, along with minerals and chemical features that appeared consistent with ancient biological activity. The announcement spread across the world within hours. Newspapers carried dramatic headlines. The National Aeronautics and Space Administration held a major press conference. Even President Bill Clinton addressed the discovery, recognizing its potential importance while urging careful scientific investigation. For a brief moment, many people believed humanity had already found evidence of life beyond Earth. But science advances through relentless testing. Over the following years, researchers examined the meteorite using increasingly sophisticated techniques. Alternative explanations gradually accumulated. Mineral growth driven entirely by geological processes could reproduce remarkably similar microscopic shapes. Features once interpreted as fossil remains no longer appeared uniquely biological. One by one, the original arguments weakened until the extraordinary claim lost broad scientific support. The disappointment left a lasting mark. Astrobiology, the scientific study of life beyond Earth, emerged from that experience with a new level of caution. Researchers recognized that nature can imitate biology in surprisingly convincing ways. From that point onward, every possible non-biological explanation had to be examined before even considering the possibility of life. The burden of proof became extraordinarily demanding. But that history explains the language surrounding every modern discovery. When researchers described Cheyava Falls, they consistently spoke of potential biosignatures rather than evidence of life. During public announcements surrounding the findings published during the year 2025, scientists repeatedly urged everyone to slow down, emphasizing uncertainty alongside excitement. Their restraint reflected decades of experience rather than hesitation. This creates an unusual tension for anyone following the search. we hear that something extraordinary has been discovered. Almost immediately, we are reminded that no conclusion can yet be drawn. Those statements can seem contradictory, yet they serve the same purpose. Scientific credibility depends upon keeping both ideas together until every alternative explanation has been tested. The lesson of Alan Hill's 84001 still shapes every careful word spoken about Mars today. A pair of ordinary looking rocks can sometimes reshape an entire investigation. That is exactly what happened when researchers took a closer look at mudstones collected inside Jezero Crater during the year 2026. These layered stones appeared modest beside towering cliffs and ancient deltas, yet they preserved one of the strongest organic records ever uncovered on Mars. The new analysis revealed hundreds of individual organic detections spread across two separate rock samples. Scientists described the results as the most robust organic detection yet recorded in Jezero Crater. Rather than relying upon a single intriguing patch, they found organic material distributed through multiple regions of both rocks. The pattern itself mattered. It suggested these compounds were woven into the ancient sediment instead of appearing as isolated contamination. To uncover that hidden chemistry, the Perseverance rover relied upon the scanning habitable environments with Raman and luminescence for organics and chemicals instrument. This sophisticated system directs carefully controlled laser light onto the rock, allowing scientists to identify both minerals and organic compounds from the way the reflected light changes. The technique creates detailed chemical maps, showing exactly where different materials are preserved within each sample. Those maps told a remarkable story. Organic carbon appeared inside both mudstones, embedded alongside minerals that formed as the sediment accumulated beneath standing water billions of years ago. Carbon serves as the primary building block for life on Earth because every known organism is constructed from increasingly complex organic molecules. But carbon chemistry alone cannot prove biology. Geological reactions, meteorites, and other natural processes can also create organic compounds under the right conditions. Even so, the setting deserves careful attention. Mudstone forms when extremely fine particles drift through calm water before settling layer upon layer across the bottom. Over immense spans of time, those soft sediments harden into rock while preserving delicate chemical signatures that faster flowing environments often erase. If microscopic organisms ever lived within an ancient Martian lake, few places would offer a better archive of their remains. Another detail surprised researchers. These mudstones belong to some of the youngest sedimentary rocks examined by the mission. Earlier ideas suggested that any traces of habitability would most likely survive within much older formations dating from the earliest chapters of Martian history. Instead, these younger deposits also contain abundant organic material, hinting that environments capable of preserving complex carbon may have persisted longer than previously imagined. But perhaps the most striking pattern reaches beyond any single outcrop. Curiosity uncovered rich organic chemistry within Gale Crater. Perseverance continues finding comparable complexity inside Jezero Crater. Different landscapes, different geological histories, and different instruments are pointing toward the same conclusion. Wherever we examine the ancient sedimentary record with enough precision, Mars continues offering complex organic molecules that refuse to remain isolated curiosities. Sometimes the greatest scientific discovery is not moving at all. It is waiting. Scattered across the floor of Jezero Crater are small titanium tubes that rest exactly where they were placed, untouched except by drifting Martian dust. They contain pieces of another world, carefully selected after years of exploration, yet they remain farther from our laboratories than ever. By the middle of the year, 2025, the Perseverance rover had operated for more than 1,500 Martian days, known as sols, while traveling farther than the length of a marathon across the crater floor and up toward its rim. Every stretch of that journey involved deliberate choices about which rocks deserved to become part of a collection unlike any assembled before. Every sample represented a question considered worth carrying across millions of kilometers, which is about 1,864,000 miles. The collection is remarkably diverse. Perseverance has gathered 27 rock cores, 2 regolith samples, meaning loose surface material made from broken rock and dust, and 1 sealed sample of the Martian atmosphere. Together, they form the most carefully curated archive of extraterrestrial material humanity has ever prepared. Every tube is made from titanium, chosen for its strength and resistance to contamination, then sealed to preserve its contents as faithfully as possible through the passing years. But those samples remain beyond our reach. Some have been placed within a carefully arranged depot on the Martian surface, while others remain stored aboard the rover itself. They were collected with the expectation that a future mission would retrieve them, launch them into orbit around Mars, and eventually return them to Earth. That ambitious chain of events has yet to receive a confirmed path to completion. The reason scientists continue waiting is simple. Rovers are extraordinary laboratories, yet they must survive violent launches, deep space travel, harsh landings, freezing temperatures, and years of remote operation. Their instruments are necessarily compact and resilient. Laboratories on Earth face none of those limits. Their powerful mass spectrometers measure atoms with astonishing precision. Electron microscopes reveal structures far smaller than visible light can resolve. Isotope ratio analyzers compare different forms of the same element to reconstruct ancient chemical histories. The difference between those facilities and rover instruments is not gradual. It belongs to an entirely different class of capability. That distinction carries enormous weight for the Sapphire Canyon sample and every other carefully sealed core. The instruments aboard Perseverance can identify compelling chemical patterns, locate promising organic compounds, and reveal environments that once supported liquid water. But only laboratories on Earth possess the sensitivity needed to determine with confidence whether those discoveries arose from geological chemistry, extraterrestrial delivery, or ancient biology. So the tubes continue waiting. They rest beneath an open Martian sky, holding fragments that could transform our understanding of life beyond Earth. Few collections have ever carried greater scientific promise. Yet today they remain exactly where they were sealed, preserved for a journey that humanity still has no confirmed way to complete. History sometimes changes through remarkable discoveries. Sometimes it changes through decisions made far from the place where those discoveries wait. While Perseverance continued sealing its carefully chosen samples beneath the Martian sky, another story unfolded back on Earth. It was a story about engineering, budgets, and a mission that gradually slipped beyond reach. The Mars Sample Return Program, developed jointly by the National Aeronautics and Space Administration and the European Space Agency, was designed to complete the final chapter of Perseverance's work. Approved during September of the year 2022, the mission originally aimed to deliver the sealed titanium tubes to Earth around the year 2033. Every rock core, every soil sample, and every atmospheric specimen collected inside Jezero Crater depended upon this ambitious plan. The architecture was unlike anything attempted before. A dedicated lander would touch down near the cached samples, a Mars ascent vehicle, meaning a rocket capable of lifting off from another planet, would launch those tubes into Martian orbit for the first time in human history. Waiting overhead, an Earth return orbiter built by the European Space Agency would capture the orbiting container before beginning the long journey home. Each step relied upon the successful completion of the one before it. But the engineering challenge carried an equally formidable financial burden. Early estimates placed the total cost between $3 billion and $4 billion. As designs matured and technical requirements expanded, projections climbed dramatically. By the year 2024, expected costs had approached approximately $11 billion. The mission remained scientifically compelling, yet many policymakers concluded that such a price could no longer be sustained, while other major scientific programs also struggled with increasing expenses. Engineers responded with a redesigned approach. During January of the year 2025, the National Aeronautics and Space Administration presented a revised proposal that reduced the projected cost to approximately $7 billion. Even after substantial savings, the figure remained difficult to justify within an already strained science budget. The redesign solved many technical concerns. It did not solve the financial reality. Then came the decisive moment. During January of the year 2026, legislation passed by the Congress of the United States effectively canceled the Mars Sample Return Program while restoring much of the remaining science budget. One flagship mission disappeared, even as many others survived. The titanium tubes remained exactly where Perseverance had left them. But the broader race did not end. China continues preparing the Tianwen-3 mission, targeting a launch during the year 2028, with the goal of returning Martian samples by the year 2031. Those samples would come from a single location rather than the carefully assembled collection inside Jezero Crater. Yet they could become the first pieces of Mars ever delivered to laboratories on Earth. That reality gives the present moment an unusual weight, the strongest collection of evidence ever assembled for answering one of humanity's oldest questions remains sealed inside titanium tubes on another planet. We know where they are. We know why they matter. Yet the mission built to retrieve them no longer exists. Imagine placing an unfamiliar stone beneath the brightest scientific light we have ever built. Every instrument agrees that something unusual is present. Every measurement deepens the mystery. Yet none can honestly say that life has been found. That restraint is not hesitation. It is the foundation upon which modern planetary science is built. The challenge begins with a difficult reality. Nearly every chemical signature produced by living organisms can also emerge through ordinary geology under the right conditions. Organic molecules can form inside living cells, yet they can also arise during chemical reactions within rocks or arrive aboard meteorites. Mineral structures can resemble fossilized microbes while forming without biology. Even gases associated with living organisms may also be generated through purely geological processes beneath a planet's surface. Because of that overlap, scientists are pursuing something more demanding than a single dramatic discovery. They are searching for combinations of evidence that collectively favor biology over every known non-biological explanation. One clue is interesting. Several independent clues pointing toward the same conclusion become much harder to dismiss. The investigation depends upon convergence rather than certainty delivered by a single observation. This approach is often described as crossing a biosignature threshold. A biosignature is any feature that may indicate the influence of life, while the threshold represents the point where multiple independent observations become collectively persuasive. No individual measurement is expected to carry that burden alone. Instead, chemistry, geology, mineralogy, and environmental history must reinforce one another until alternative explanations become increasingly improbable. That perspective explains why Cheava Falls continues to command such attention. The site occupies perhaps the most compelling category in all of Mars exploration. It has not provided evidence that life certainly existed. It has revealed evidence worthy of the full machinery of life detection science. Each new observation strengthens the case for further investigation without allowing responsible scientists to claim more than the data genuinely support. But what would finally move that evidence across the threshold? Researchers would want isotope analysis capable of showing whether the carbon inside the rock carries patterns associated with biological processing rather than ordinary chemistry. They would examine mineral structures in extraordinary detail, asking whether their arrangement could reasonably arise without living systems. They would also analyze complex organic compounds, determining whether their composition resembles biological production more closely than delivery by meteorites or geological reactions. Every one of those investigations requires laboratories on Earth. Their instruments exceed the sensitivity of rover technology by many orders of magnitude, allowing questions to be explored at levels impossible on another planet. The difference is profound. That is why the loss of a confirmed path for returning the Martian samples reaches far beyond budgets or schedules. It delays the only experiments capable of answering the deepest questions raised by Cheava Falls. The tubes remain sealed, the evidence remains beyond reach, and the strongest opportunity yet to determine whether Mars once hosted life continues waiting, suspended between remarkable discovery and unanswered possibility. The meaning of a habitable world has changed more than almost any other idea in planetary science. As we continued exploring our own planet, the boundaries that once seemed fixed gradually dissolved. Mars itself did not become warmer or wetter during those decades. Our understanding of life simply became much larger. During the 1970s, many researchers believed living organisms required familiar surroundings. Warm temperatures seemed essential. Sunlight appeared indispensable. Liquid water at the surface was considered a basic requirement, along with abundant organic nutrients. Under those assumptions, Mars looked barren beyond reasonable doubt. Few expected the planet to offer anything that biology could use. But everything shifted in the year 1977. Oceanographers discovered hydrothermal vents deep beneath Earth's oceans where scorching mineral-rich water poured from fractures in the seafloor. Entire ecosystems flourished there despite complete darkness. No sunlight reached those depths. Photosynthesis played no role. Instead, tiny organisms drew energy directly from chemical reactions between water and rock, supporting larger creatures through an entirely different foundation for life. That discovery changed expectations. It also encouraged scientists to search in places that once seemed pointless. New surprises followed. Researchers found microbes enduring the crushing dryness of the Atacama Desert, surviving within microscopic films of water hidden inside rocks. Other communities lived in the dry valleys of Antarctica, remaining active inside mineral crystals despite temperatures reaching minus 20 degrees Celsius or minus 4 degrees Fahrenheit. Some organisms thrived in boiling acidic pools with an acidity level once thought impossible for life. Others persisted inside cooling ponds surrounding nuclear reactors. Still more occupied the deepest ocean trenches beneath pressures that would instantly destroy familiar surface organisms. Each discovery widened the map. Every expedition rewrote another assumption. But the pattern became even more intriguing when scientists reconsidered conditions found on Mars. Perchlorate salts had long been viewed as obstacles because they are highly reactive chemicals capable of disrupting many biological processes. Later studies revealed Earth microbes that actually use perchlorate during their metabolism, gaining energy from compounds previously regarded only as hazards. A seemingly hostile chemical environment suddenly appeared less definitive than before. Radiation offered another example. The Martian surface receives levels that would severely damage the human body over time. Yet Earth is home to bacteria capable of surviving radiation exposures, thousands of times greater than what would prove fatal for a person. These remarkable organisms repair shattered genetic material with extraordinary efficiency, demonstrating that biology can adapt in ways once considered impossible. None of these discoveries prove that Mars ever supported life. They reshape the question itself. Conditions once dismissed as absolutely incompatible with biology now resemble environments already occupied somewhere on Earth. But that shift carries profound consequences. Everywhere scientists have searched across our own planet for life, they have eventually found it. Every proposed boundary has slowly retreated. With each retreat, another piece of Mars moves from impossible toward plausible, inviting us to look again with humbler expectations and far sharper tools. Perhaps the deepest possibility is not that Mars once hosted life, but that neither planet ever began its story alone. Instead of imagining two separate origins, we can consider a universe where biology, or the ingredients that make biology possible, drifts from world to world across immense stretches of time. This idea is known as panspermia. It is the hypothesis that living organisms, or the chemical precursors that eventually become life, can travel between planets inside pieces of rock launched into space by enormous impacts. At first, the proposal sounds extraordinary, but the exchange of planetary material is no longer speculative. It is an observed consequence of violent collisions throughout the history of the solar system. Mars and Earth have spent billions of years throwing fragments at one another. When a large asteroid strikes a planetary surface, the tremendous energy can blast rocks completely free of the planet's gravity. Most wander through space indefinitely. A tiny fraction eventually collides with another world. More than 200 meteorites discovered on Earth have been confirmed as originating from Mars because the gases trapped inside them precisely match the composition of the Martian atmosphere. But could anything alive survive such an unimaginable journey? Experiments suggest the answer may be more encouraging than once believed. Certain bacteria have endured prolonged exposure to the vacuum of space while protected inside rock. Others have survived intense radiation far longer than earlier estimates predicted. Even the fiery plunge through an atmosphere does not necessarily sterilize an entire meteorite. The exterior becomes intensely hot, yet the interior can remain comparatively cool, preserving material buried deep within the stone. That possibility transforms the relationship between our worlds. Life could have emerged on ancient Mars before reaching Earth aboard wandering rocks. The opposite sequence is equally plausible, with early Earth sending microscopic passengers toward Mars. There is also a broader possibility. Both planets may have inherited life's earliest ingredients from somewhere else entirely, receiving them from distant objects long before either world resembled its present form. But this creates an unexpected complication. Imagine that future explorers finally uncover living organisms beneath the Martian surface. Would that prove life emerged twice in the universe? Perhaps not. If Martian organisms share a common ancestor with Earth's biology, then we would be discovering another branch of the same ancient family rather than an entirely separate origin. That is why astrobiologists examine chemistry with extraordinary care. They want to know whether Martian biology, if it exists, relies upon the same deoxyribonucleic acid, the same collection of amino acids, and the same molecular handedness, meaning the preferred three-dimensional arrangement of biological molecules that every known organism on Earth uses. Shared chemistry could point toward a common ancestry. A fundamentally different biological system would suggest something even more profound. It would imply that life is not a singular accident, but a process the universe is capable of beginning more than once. One gas continues to drift through every discussion about Martian life, refusing to settle into a simple explanation. Methane is remarkably fragile in the Martian atmosphere. Sunlight and chemical reactions gradually destroy it over time, meaning any methane detected today must have been released relatively recently. Something is replenishing it. We simply do not yet know what that something is. But the discoveries we have explored reshape how we interpret that mystery. If microscopic organisms are producing Martian methane, they almost certainly do not inhabit the exposed surface. They would be expected far below it, where geological heat may still maintain liquid water and where radiation no longer dominates the environment. There, methanogens, meaning microbes that generate methane as part of their metabolism, could survive without oxygen, without sunlight, and without organic nutrients. They obtain energy from hydrogen and use carbon dioxide as their source of carbon, making them especially well suited to deep underground environments. That possibility has moved beyond theoretical discussion. Since the year 2003, researchers have designed laboratory experiments using simulated Martian soil to investigate whether methanogenic bacteria could remain active under Martian conditions. 4 different strains have been tested. All produced substantial quantities of methane, even when the soil contained 1% perchlorate, the reactive salt once assumed to be overwhelmingly hostile to biology. Laboratory success does not demonstrate that Mars contains living methanogens. It establishes something equally important. The chemistry of modern Mars does not automatically exclude them. But another clue has continued to attract attention. Measurements gathered over many years indicate that Martian methane varies with the seasons, reaching its highest concentrations during the warmer months. You might expect biology to respond to changing temperatures in exactly that way. Yet, temperature also alters purely geological processes. Heating and cooling can influence how gases move through fractured rock and frozen ground. Both explanations remain consistent with the available observations. Neither has been ruled out. Additional evidence points toward another possibility. The European Space Agency mission, called Mars Express, identified tectonic faults extending beneath a region believed to contain shallow buried ice. Permafrost, meaning permanently frozen ground, forms an effective seal that can trap gases beneath the surface for immense periods. As temperatures shift or underground pressure changes, methane stored below that frozen layer could escape through deep fractures, producing intermittent releases without requiring any biological source. The puzzle, therefore, remains balanced between 2 credible possibilities. Curiosity can continue measuring methane, but it cannot determine its ultimate origin with certainty. Solving that mystery will require a spacecraft specifically designed to trace methane back to its source beneath the surface, or detailed isotopic analysis, meaning measurements of different forms of carbon that can reveal how a gas formed. Those extraordinarily sensitive tests belong in laboratories on Earth. Once again, the path toward an answer leads back to the sealed samples waiting on another world. Scientific ideas rarely disappear all at once. They often fade into the background, waiting for new evidence to cast familiar discoveries in a different light. That has been the strange journey of the Martian meteorite, known as Allen Hills 84001. Although the excitement surrounding it diminished after the late 1990s, the rock itself never changed. It continued to preserve the same structures, minerals, and organic compounds that first captured worldwide attention. Most researchers gradually accepted that the apparent fossil evidence could be explained without biology and turned toward newer missions on Mars. But a smaller group continued examining the meteorite with increasingly sophisticated techniques. Their work did not restore the original claim. Instead, it complicated the confidence with which that claim had been dismissed. Among the most debated features are the polycyclic aromatic hydrocarbons, a family of organic compounds made from interconnected rings of carbon atoms. These molecules can form through biological activity, yet they can also arise through entirely natural geological processes. Some investigators argue the compounds entered the meteorite after it landed in Antarctica, carried by contamination from the surrounding environment. Others point out that their distribution deep within the rock does not match the pattern expected if contamination had simply seeped inward over time. The disagreement has endured because both interpretations remain plausible. But the discussion extends beyond those organic compounds. Tiny carbonate globules inside the meteorite, meaning rounded mineral deposits formed long before the rock reached Earth, contain microscopic crystals of magnetite. These crystals resemble structures produced by certain bacteria on Earth. Several purely geological mechanisms have been proposed to explain their formation. Yet none has gained universal acceptance as a complete explanation for every observed characteristic. The resemblance therefore remains intriguing without becoming conclusive. This renewed attention has also influenced how some scientists reconsider much older results. Researchers who believe Mars has been judged too harshly argue that the Viking landers may have detected biological activity after all. They note that later missions identified organic molecules across multiple Martian locations, discoveries that challenge the earlier assumption that the planet was essentially devoid of organic material. If Vikings' instruments were limited by the chemistry of the Martian soil, some of their most controversial findings deserve another careful reading. You can see a pattern emerging. Individual mysteries that once seemed isolated now intersect with one another. Meteorites, rover discoveries, laboratory experiments, and decades of planetary exploration increasingly form parts of the same unresolved picture rather than disconnected episodes. But none of this transforms Allen Hills 84001 into proof of ancient Martian life. It remains a deeply contested piece of evidence. Its lasting importance lies elsewhere. The history of Mars astrobiology has never been a series of ideas cleanly discarded. Instead, it has become a growing collection of increasingly complex puzzles, each new discovery forcing us to revisit earlier conclusions with greater care than before. As our search gradually widened, Mars stopped looking like a lonely exception. Instead, it became one destination within a growing collection of worlds that seems surprisingly welcoming to chemistry, water, and perhaps even biology. you begin to notice a remarkable shift. The question is no longer whether our solar system contains places that might support life. The question has become how many such places have been hiding in plain sight. One of the strongest candidates circles the giant planet Jupiter. Europa appears frozen from above, yet measurements gathered by passing spacecraft reveal something extraordinary beneath its fractured shell. A global ocean of liquid water stretches below the ice, estimated to reach between 60 kilometers, which is about 37 miles, and 150 kilometers, which is about 93 miles, in depth. That hidden ocean contains more liquid water than all of Earth's oceans combined. It remains unfrozen because Jupiter's immense gravity continually squeezes the moon, creating internal heat through a process called tidal heating, meaning repeated flexing that warms the interior. But another moon has become equally compelling. Enceladus, orbiting Saturn, repeatedly launches towering plumes of water vapor through fractures near its south pole. Those icy geysers have been sampled directly by spacecraft flying through them. The material contains hydrogen, silica particles, and complex organic molecules. Together, they point toward hydrothermal activity, meaning hot water reacting with rock on the ocean floor. On Earth, such environments support thriving ecosystems completely independent of sunlight. The comparison is impossible to ignore. Then our attention turns toward Titan, Saturn's largest moon, where the landscape challenges nearly every expectation we have built from our own planet. Rivers flow there, lakes spread across the surface. Rain falls from the sky, yet the liquid filling those channels is methane rather than water. Above them hangs a thick atmosphere dominated by nitrogen. Beneath the frozen crust, many scientists suspect another ocean of liquid water may exist. Titan invites us to imagine whether biology could emerge from a chemistry unlike anything familiar, using methane where Earth relies upon water. But these worlds do more than expand a list of destinations. They reshape our understanding of what it means for a place to be habitable. Half a century ago, scientists believed such environments were exceptionally rare. Each new mission has steadily weakened that assumption. Oceans hidden beneath ice, underground reservoirs warmed by rock, and chemically active landscapes continue appearing across the solar system. Mars therefore occupies a different place in the story than it once did. It remains one of the most accessible worlds where ancient or surviving life could still be found, yet it no longer stands alone. As we continue exploring, the solar system increasingly resembles a neighborhood filled with promising habitats, suggesting that nature may create opportunities for life far more readily than we once believed. The road ahead is no longer defined by a single mission. It has become a collection of possibilities, each carrying a different piece of the same enduring question. As you follow the future of Mars exploration, certainty gives way to overlapping plans, ambitious proposals, and timelines that continue to shift with technology, budgets, and international priorities. One of the most closely watched efforts belongs to China. The Tianwen-3 mission is currently targeting a launch during the year 2028, with the goal of delivering Martian surface samples to Earth around the year 2031. If everything succeeds, it could become the first mission ever to return material directly from Mars. The samples would come from a single landing location rather than the carefully selected collection assembled by Perseverance. But even a limited return would represent a historic achievement, providing laboratories on Earth with fresh Martian material for the first time. Europe is preparing another important step. The European Space Agency's Rosalind Franklin rover was designed with a capability unlike any rover operating on Mars today. Its drill can reach 2 meters, which is about 6.6 feet, beneath the surface, extending below the layer most heavily altered by billions of years of cosmic radiation. That protected depth offers a far better chance of preserving ancient organic material. Instead of relying only on surface rocks, the rover would investigate material that has remained shielded for immense stretches of Martian history. But other ideas remain on the drawing board. The National Aeronautics and Space Administration has studied the Mars Life Explorer concept, a mission created specifically for life detection rather than general geological exploration. The proposal includes drilling into ice-rich permafrost, meaning permanently frozen ground that may preserve ancient chemistry, while searching directly for amino acids, the molecular building blocks used by proteins in living organisms, along with possible cellular structures. It represents a focused attempt to answer the biological question rather than simply gather more environmental evidence. Commercial space companies have also entered the discussion. Following the cancellation of the government-led Mars Sample Return Program, several private proposals emerged to reduce costs through simpler mission designs. Among them is a fixed-price concept developed by Rocket Lab, suggesting that smaller launch systems and streamlined engineering could make returning Martian samples financially achievable. These ideas remain proposals rather than approved missions, yet they demonstrate that alternative paths are still being explored. But honesty remains essential. None of these efforts is guaranteed to fly as currently envisioned. Funding decisions change, technical challenges appear, political priorities shift. Every mission still depends upon years of development before a rocket ever leaves Earth. So we find ourselves in an unusual moment. The evidence continues to accumulate, the technology steadily improves, and the destinations are already chosen. Yet the decisive experiment, the one capable of transforming the search for Martian life into a definitive scientific answer, still waits for a future that has no confirmed arrival date. Sometimes the smallest discovery reshapes the largest question. A single microbe preserved inside an ancient rock would seem insignificant beside the scale of the cosmos. Yet its existence could force us to rethink everything we believe about life beyond Earth. As our journey expands outward once again, Mars becomes part of a much greater mystery that stretches across the observable universe. Astronomers call this mystery the Fermi paradox. It begins with an unsettling observation. The universe is approximately 13.8 billion years old. It contains hundreds of billions of galaxies, and each galaxy holds hundreds of billions of stars. Around many of those stars orbit planets that appear to exist within regions where temperatures could allow liquid water to remain stable. Given such astonishing numbers, you might reasonably expect life to have emerged many times. If so, where is everyone? Two broad possibilities have dominated the discussion for decades. One suggests that life is extraordinarily rare, requiring such an unlikely combination of chemistry, timing, and planetary history that Earth may represent one of very few successful examples. The other proposes something very different. Life may be widespread, while immense distances, limited technology, or the fundamental nature of communication prevent civilizations from recognizing one another across the depths of space. But Mars occupies an extraordinary position within this debate. Long ago, it possessed rivers, lakes, groundwater, volcanic energy, and a thicker atmosphere. Its habitable conditions probably lasted for hundreds of millions of years before the planet gradually transformed into the colder world we know today. If life managed to emerge there independently despite that shorter and more difficult history, then biology may arise wherever circumstances become even briefly favorable. That possibility would suggest a galaxy filled with living worlds. The opposite conclusion carries equal weight. If Mars never produced life, despite once possessing many ingredients considered essential, then perhaps the leap from chemistry to biology is vastly more difficult than we currently imagine. Earth could represent an exceptional outcome rather than a common one. Our neighboring planet, therefore, becomes far more than another destination for exploration. It becomes a natural experiment conducted across billions of years. You can begin to appreciate why every new Martian discovery attracts such careful scrutiny. The search is no longer focused on one planet alone. Each rock, each organic molecule, and each promising biosignature contributes to a much larger calculation about the universe itself. But the deepest significance lies in a remarkably simple idea. A single inhabited planet tells us almost nothing about how often life appears because we have no comparison. Two inhabited planets would change everything. Even if both existed within the same solar system, they would reveal a pattern rather than an isolated event. And once a pattern exists, the immense darkness between the stars begins to look far less empty than it once seemed. Across laboratories and universities, years of careful preparation now rest beside an unanswered question. Entire careers were built around the expectation that the sealed samples from Mars would eventually reach Earth. Researchers devoted decades to designing instruments, refining contamination controls, and preparing experiments that have never been performed. Some of those scientists are now in their 60s and 70s. They understand that the answer they have pursued for much of their working lives may arrive long after they are gone. But the samples continue to wait. Among them rests the tube containing material collected from Sapphire Canyon. Its contents remain sealed exactly as they were gathered by Perseverance. Nothing inside has changed. The rock has neither become stronger evidence nor weaker evidence. It simply remains beyond the reach of the laboratories capable of asking the next questions. Day after day, the tube sits upon the Martian surface, exposed to radiation, surrounded by a landscape shaped billions of years ago. It rests within the remains of an ancient riverbed, preserved in the cold darkness of another world, waiting for hands that may not arrive for many years. That waiting carries consequences extending far beyond one mission. Every unanswered measurement delays countless others. Each uncertain result slows new theories, future spacecraft, and the broader search for life across the solar system. Science advances through evidence, gathered step by step. When one essential step disappears, many paths forward become narrower. But the deepest cost reaches beyond planetary science. We still do not know whether life emerged only once or whether the universe repeatedly discovers the same solution wherever suitable conditions appear. Without that knowledge, we cannot estimate how unusual our own existence may be. Are we witnessing an extraordinary exception, or are we one expression of a process written into the fabric of matter itself? The difference changes how we understand our place in the cosmos. If life proves exceptionally rare, then every forest, every ocean, and every living species on Earth becomes part of something almost unimaginably precious. If life proves common, then we inhabit a universe where biology flourishes whenever chemistry is given enough opportunity. Either answer reshapes humanity's perspective. Neither answer leaves us unchanged. You can feel the weight of that uncertainty. It extends beyond curiosity. The question touches every branch of biology, astronomy, geology, and philosophy at once. It also reaches into our choices about exploration, preservation, and our responsibility toward the only inhabited world we presently know. But the central question remains exactly where it has always been, resting inside carefully sealed titanium tubes on Mars. Until those samples reach laboratories capable of revealing their full story, we remain suspended between two profoundly different visions of reality, unable to say whether life happened once by remarkable fortune or whether the universe has been creating it all along. Look upward on a clear evening, and you may notice a small reddish light drifting among the stars. It does not flicker as strongly as they do. Instead, it moves with steady purpose, tracing its own path across the changing sky as the seasons pass. Long before we understood that this distant point was another world, you and I would have seen exactly the same light that generations before us watched with equal fascination. Every civilization gave it meaning. The ancient Babylonians carefully followed its wandering course and wove its crimson glow into stories of powerful gods. The ancient Egyptians called it Har-Desher, the Red One, preserving its appearance in a name that endured for centuries. Much later, medieval astronomers measured its motion with increasing precision, using its changing position to challenge and refine humanity's understanding of the solar system. For most of history, Mars remained only that distant light. It could not be visited. It could not be touched. Its reddish color encouraged associations with blood, conflict, and divine power because no one possessed another explanation. Across thousands of years, the planet invited imagination far more easily than observation. But our relationship with that distant light has transformed beyond anything our ancestors could have imagined. We have landed robotic explorers upon its surface. We have watched blue sunsets spread across its dusty horizon because fine Martian dust scatters sunlight differently from Earth's atmosphere. We have listened to recordings of wind moving across another planet. We have observed dust devils winding over empty plains, drilled into ancient rocks, and sealed carefully chosen pieces of that history inside titanium tubes. Yet the central mystery remains. Despite every photograph, every measurement, every successful landing, and every remarkable technological achievement, we still cannot say with confidence whether Mars ever hosted life. The planet has become deeply familiar in many ways. Its valleys have names. Its mountains have been measured. Its seasons are understood. But its biological history continues to resist every attempt at a final answer. But that uncertainty should never be mistaken for failure. It reflects the extraordinary challenge before us. Mars is a real world, orbiting the same star as Earth. At its greatest distance from us, it lies about 225 million kilometers away, which is about 140 million miles. Across that immense gulf, we are attempting to reconstruct events that unfolded billions of years ago using patient engineering, careful mathematics, and machines operating without human hands. When you consider that distance, the progress itself becomes remarkable. We have crossed the emptiness between worlds, with ideas first, then with spacecraft, then with laboratories built from metal and code. The pale red dot that once inspired myths now offers evidence instead. Even so, it continues to remind us that the greatest discoveries often wait beyond the edge of what we can presently reach. Imagine for a moment that the long search finally reaches its answer. A laboratory completes its analysis. Independent teams repeat the work. Every competing explanation falls away until only one remains. The evidence shows that life once existed on Mars, perhaps billions of years ago, preserved inside a rock that waited longer than human civilization itself. The following morning would look almost ordinary. Cities would awaken. Children would leave for school, airplanes would cross familiar skies, oceans would continue their tides, and forests would continue their seasons. No mountain would move, no law of physics would change. The discovery would not alter the practical rhythm of daily life. Yet beneath every ordinary moment, something far deeper would have shifted forever. We would no longer see Earth as the single known place where chemistry awakened into biology. Instead, we would know that the same universe produced life twice within one modest planetary system. That realization would reach far beyond Mars. It would reshape the assumptions beneath astronomy, biology, and our understanding of existence itself. But consider what Mars would be telling us. It possessed a shorter period of habitability than Earth. Its magnetic field faded early, exposing the surface to intense radiation. Its smaller mass allowed much of its atmosphere to escape into space. Gravity held the planet less tightly, and liquid water gradually disappeared from the surface. If life still managed to emerge under those conditions, then perhaps life is not an astonishing accident balanced upon impossibly narrow circumstances. Perhaps it is simply what chemistry does when matter is given enough time and opportunity. That possibility expands outward, almost without limit. Europa's hidden ocean becomes even more compelling. The water erupting from Enceladus deserves greater urgency than ever before. Every distant planet with suitable conditions begins to resemble a place where biology may already have written its own history. Suddenly, countless worlds become more than interesting landscapes. They become possible homes for living systems. The feeling we call cosmic loneliness would also begin to change. For generations, we have wondered whether consciousness exists anywhere beyond Earth, while surrounded by a universe containing hundreds of billions of galaxies, each holding hundreds of billions of stars. If life appeared twice within our own solar system, isolation begins to look less like reality and more like the temporary consequence of limited reach. But the opposite conclusion carries equal weight. Suppose Mars proves completely sterile, despite its rivers, lakes, minerals, and ancient chemistry. Suppose every promising clue ultimately leads nowhere. Then Earth becomes more extraordinary than we have yet allowed ourselves to believe. We would be forced to consider that life may require circumstances so uncommon that an inhabited planet is among the rarest creations the universe can produce. Either answer transforms us. The discovery itself matters because it reveals what kind of universe you and I have always inhabited, whether life is a remarkable exception or one of nature's deepest and most enduring patterns. Somewhere within the ancient channel of Neretva Vallis, a single rock continues its long vigil. It has remained there for about 3.5 billion years, unchanged by every chapter that followed. It endured the fading of a thicker atmosphere, the disappearance of surface water, the relentless arrival of cosmic radiation, and the freezing darkness that returns with every Martian evening. While Earth filled with bacteria, forests, dinosaurs, mammals, and eventually people capable of reaching another planet, that stone simply remained where it was. Beside it rests a titanium tube. Inside lies a carefully drilled core taken from the rock's interior, sealed against contamination and catalogued with extraordinary precision. It belongs to a collection unlike any humanity has ever assembled. Every sample was chosen because it might preserve a fragment of Mars that no instrument carried by a rover can fully explain. Whether those tubes ever leave the planet remains uncertain. But on Earth, the search continues in another form. Researchers still gather at conferences, debate isotope measurements, refine laboratory techniques, and write proposals for missions that have yet to receive approval. many believe the answer is within reach. The challenge is no longer only scientific. It has become political, financial, and dependent upon choices made far from the laboratories that would eventually examine the samples. Elsewhere, within official government records, the mission intended to retrieve those tubes has already become part of history. Funding disappeared into changing priorities, while discussions increasingly turned toward the distant goal of placing human explorers upon the Martian surface. Those ambitions remain inspiring, yet the unanswered samples continue waiting without regard for shifting plans. The question itself belongs to none of these events. It remains patient. Did life ever emerge on Mars? If it did, was it extinguished billions of years ago, or could something still persist beneath the surface, where buried water, gentle warmth, and slow chemical reactions may continue beyond our view? We cannot yet answer. The uncertainty belongs to the evidence, not to a lack of determination. We have never stood closer to knowing than we do today. Yet progress toward that knowledge has slowed for reasons that reach beyond science itself. But the question does not fade with time. The samples remain protected inside their titanium tubes. Deep underground, hidden environments continue whatever processes they have followed for immense spans of history. Seasonal methane continues to appear and disappear, intriguing, elusive, and still without a universally accepted explanation. Mars has never concealed its story through intention. It simply exists at a distance that, at its greatest separation from Earth, reaches about 225 million kilometers, which is about 140 million miles. Across that vast expanse, the planet continues to wait, holding its history with the same patience it has shown for billions of years, until one day we are finally able to listen closely enough to understand it.